Hello everyone and welcome to the today's session. Dear Sir, on behalf of School of Civil Engineering, Lovely Professional University, Indian Geotechnical Society, IGS, Jalandhar, Chapter and Department of Civil Engineering, Dr. Bhimrao Ambedkar, National Institute of Technology, Jalandhar. I welcome you for your session on the topic Simple Approach to Assess the Load versus Settlement for Shallow Foundation. This session is chaired by Dr. Amit Srivastava, Professor and Head of School of Civil Engineering, LPU, and will be co-chaired by me, Pranjal Verma, the student of School of Civil Engineering and my faculty. Now I request my faculty member, Dr. Amit Srivastava, to take over the session and start the proceeding.
Thank you, Pranjal, for this nice introduction. And let me take this opportunity to introduce Dr. Yang to the audience who have joined us on this Google Meet platform. Uh, Dr. Yang joined the Department of Civil Engineering at West Virginia University Tech in 2011. Dr. Yang received his undergraduate civil engineering degree from Chung Yung University and his MS from National Pingtung University of Science and Technology in Independent Taiwan. Before leaving his homeland, Dr. Yang practiced as a manager of the Civil Engineering Service Center at NPUST and served as a lieutenant in the Taiwan Army Corps of Engineers. Dr. Yang later earned his Ph.D. in Geotechnical Engineering from the University of Nevada, Reno in 2005. After obtaining his Ph.D., Dr. Yang served as a lecturer and manager of the Geotechnical Engineering Laboratory at UNR. While there, he taught geotechnical engineering courses both at the undergraduate and graduate levels and participated in soil liquefaction research. Dr. Yang also performed research on large-scale soil structure interaction under simulated earthquake motions. Dr. Yang's other research interests in geotechnical engineering include soil property characterizations, large-scale soil structure interaction, in situ soil testing, and geotechnical earthquake engineering. Dr. Yang is a registered professional engineer in the state of Nevada and a member of the American Society of Civil Engineers and the Earthquake Engineering Research Institute. Thank you very much, sir, for being with us and sparing your time with us for this nice presentation on simple approach to assess the load versus settlement for shallow foundation. I hand over the session to you. During the session, if you have to the audience, this is just a notification that if you have any question, you can write in the chat box, or you can ask the question at the end by unmuting yourself. So your questions will be taken care by the expert at the end. Till then, it is requested that keep yourself muted and your video should also be turned off. Over to you, sir.
Thank you. All right. First of all, I'm very honored to be invited to this conference, and I really like to thanks for Dr. Srivastava and very detailed introduction, and also Mr. Verma, the very nice organized for this conference. First of all, I just want to introduce myself a little bit since this is an international conference. So I believe a lot of audience is from the different country, different places. Actually, right now I'm in the West Virginia. If you see the screen right now, I'm just right here. Okay, so we are somewhere between Virginia. Well, we are west side of the Virginia, so a lot of people think of West Virginia is a part of Virginia, but actually no, we are another state. So we are between the Kentucky, Ohio, this kind of a region. And well, you probably already know the Texas right now is in trouble because these icy cold, very cold temperature effect. But this storm right now is actually just past our West Virginia. So we have a little bit issue. Actually, last night I'm still worrying about my internet stabilization because internet is on and off, and also power is on and off. And I try to go to my office because maybe my infrastructure in the office is much better than my house. But unfortunately, I couldn't get out of the house. It is the completely road condition still in a big mess. So if unfortunately my internet disconnect or my power is off, that's the worst of the worst. And hopefully you understand that this critical time in East Coast of the entire U.S. it's not easy. Okay, so I just want to pass my greeting from West Virginia all the way to India. And I think from internet, I searched the school over there. I think you are somewhere right here. Okay, so hopefully I'm in the point out the right position.
Yeah.
Okay.
Yeah.
Anyway, yeah.
Perfect.
Okay. That's actually a very critical position. Well, you are so close to Pakistan, so close to China, so it's something between. So it's kind of tension, I believe. But hopefully everybody is peaceful and healthy.
Yeah.
Okay, let's move on. To my next slide. I think I already have a really detailed introduction, but I just wanna just go over some of my background. And actually today the topics I try to present is not my long-term research goal, but I originally think about to present something related to the earthquake engineering, which I'm good at. But unfortunately, I still have some data. I'm cooperate with some of the professor in Turkey, University of Ankara, and also my advisor in Nevada. A lot of data we haven't put it together and present very successful result yet. So I have to switch my the topics to the other one. I get involved, but most likely the main credit I have to give my advisor, Dr. Gary Norris. So I just wanted to let you know that I'm original from Taiwan. I finished my master and undergraduate degree in Taiwan, and I moved to U.S. in about 1998. But I was in one of the university in Chicago. They call IIT. I remember that I have some friend in India. They said, "Well, you are from IIT." I said, "Okay." Well, it seems like there's a very good school in India also called IIT. So I was there for a year, but I couldn't finish my degree over there because of scholarship issue. So I go to the University of Nevada, Reno, and from there I get my degree, and I teach there for another 6-7 years, and I moved to West Virginia. Okay. So now I just want to give the big credit to my advisor, Dr. Gary Norris. And this whole presentation actually is start from his long-term contribution about something he is doing, not only just earthquake engineering, and also something related to the pile foundation, shallow foundation, and some soil behavior. Dr. Gary Norris, he already retired, but he's still working very hard to try to accomplish his long-term goal, I would say that way. Long-term goal. The Dr. Norris also very active right now in some of the research project. He's a straight up UC Berkeley person, so he's kind of like a genius actually. Maybe in the next year I can invite him, or the conference can invite him to give a talk down the road. Dr. Gary Norris finished all his degree in Berkeley, and he teach in the University of Wisconsin-Madison for only 2 years, but because they are from California, so his wife is really afraid about the cold weather in Wisconsin, so they moved to Reno to take the position over there until he retired in 2008. And actually, this is all his a lot of different research he's doing in the entire 25 to 28 years. Okay, all right, so let's move on to my main topics, talking about some, well, the one we are trying to talk about today is basically more like an idea sharing, because we still need to have more data to prove what we are doing. But those, the field tests cost a lot of money, and it's not easy to get it through. And I will explain some of the problem we have right now and some of the result we have. But we only publish those results in some of the conference. One paper is trying to push it through the journal, but we have some of the challenge from the different expertise. So we need to keep working on this kind of project. Okay, so let's get into the issue we have. All right, so bearing capacity. So this is like a foundation engineering 101. So what we try to accomplish is, if you see the equation we have right here, let me try to bring my marker so I can write something here. All right, so I believe everybody see this equation all the time, and start from your undergraduate degree, probably the senior years. When we're talking about foundation engineering, the first equation you are seeing is the bearing capacity, the shallow foundation bearing capacity. So these three terms we are talking about right here, I put a lot of the factor in the back. It is actually the different opinion about how they do the modify to the equation. So you will see the hierarchy, probably the people, everybody is supposed to be using the hierarchy, the formula all the time. Might have Hansen and Basic. Those four people, it is probably right now is the mainstream of the bearing capacity for all the different research. And I just put everybody's opinion in the backhand side right here, but I will go through a little bit detail later. But anyway, so this is my main goal. So from very, very complicated bearing capacity formula we saw before, and we try to simplify and go back to the fundamental using only the Mohr circle behavior to predict the bearing capacity and plus some settlement. Okay, all right, so that's my main goal. All right, I want to emphasize the one we're talking about, the bearing capacity, is not including the local shear or Pingtung shear. It's only talking about the general shear, which means when the foundation is completely failed, it's supposed to generate the entire the spiral, the entire spiral. So what we are talking about it is we try to come up a simple solution to replace this kind of the general fail of the bearing capacity. Okay, so once again, this the three term is talking about all the resistance along the spiral, Okay, all right. Now let's talk a little bit detail about the four different equations come up from these four famous people. Taraki, of course, he start from 1943. He's come up this simple equation we are seeing right here. Everybody see this long time ago. And he also introduced some of the correction factor from the different shape of the foundation. So he start from the straight footing, and then they do some correction for the round footing and the square footing. And might have actually have some other opinion about, well, the different the correction factor. Okay, so he introduced what we call the depth factor, the shape factor, and also the most important is how to introduce some of the inclined load. So we are not expecting the foundation only carry the vertical load. It could be the load is from some inclined angle. So that's one of his contribution. Hansen, the other side, he actually used a lot of idea from the Myhab and Taraki, but he also introduced something else, especially his the factor, bearing capacity factor is quite different right here. And basic is the same. Basic is actually expand everybody's, but he has his own opinion about the different correction factor. Okay, let's talk a little bit detail for the different factor. As I just mentioned, the main contribution for the MyHub is he start to introduce what we call the shape factor, the depth factor, and inclined angle factor. So I think everybody see the textbook. This is all the correction factor they are talking about. Okay, so you can see the formula start from CNC, QNQ, half B, gamma, N, gamma, and now expand a little bit more with these three different correction factor for each formula. And also the Hansen, I think he's introduced what we call the slope factor. That means they are trying to talking about if my footing instead of sit on the flat surface, and what if my foundation is sit on the slope. So he introduced this particular, they call a slope factor. All right, so the slope factor, it's a bunch of stuff right here. Okay, and the other one is what? It could be your foundation instead of entire flat. It could be your foundation maybe have some of the tip over angle like this. Okay, so he also have some tile the best factor. So it's all going now. Okay, and basic also have the similar as a Hansen, but this is his major difference. He have a different bearing capacity, the factor to change the N gamma. So this is his main difference. And also he have a different opinion about the incline angle, the ground incline angle, and the footing. So I just put a bunch of stuff right here. I would like to share this PowerPoint slide if some of you may be in the research about the bearing capacity. I think I kind of put everything together, so it will be very convenient for you to jump in between the different correction factors. Okay, now let's talk of just put everybody together. So you can see that it doesn't matter is a shape factor, the depth factor, or incline angle factor, and pretty much everybody have the different opinion. But so far you can see that none of them is really have any large scale test to identify their correction factor is correct or not, right? So this is something it's always in a big black box. I would say that way. Okay, now so no matter what, something they understand, something's different. The main goal it is what those bearing capacity factor at least these two is all the same. These two is all the same. The only difference is what the N gamma. This term you can see that my half he using this formula, the Hansen using that formula, and the basic is using that formula. Somebody? Okay. Well, anyway, everybody have a different opinion about this. So I kind of like using whatever the NQ it is. You can see this one is -1, this one is +1. So whatever it is, just leave as it is. But the major difference is in the backhand side right here. Some people say it's a tangent 1.4 friction angle. Some people using this, some people use that. Well, anyway, I just put a J right here to replace those three terms. And there will be slight difference if you take a look this chart. If you put the different friction angle, and you can see the N gamma from the different three opinion. These two almost the same. This is quite different. Okay, here's 0.1, 0.1, here's 0.4. It's 4 times different. 0.4, 0.4, 1.2, 3 times different. Okay, so the basic, this one, it's quite different. It's quite different. Okay, it's very interesting, but this is what it is. All right, so let's talk about some of the issue we have from the field. Well, normally when you come up with a formula and you want to prove your formula is useful, reliable, or accurate compared to the field. Geotechnical engineering, one of the things is very interesting is you never have any soil condition it's exactly identified. So it's hard for the field test. A lot of different opinion, a lot of different soil condition. So it's very hard to conduct a field test. But another big issue we have, if you take a look at the picture I'm showing you right here, if you want to run the field test, so let's see that if you want to have a footing, and if you try to push the footing and try to force the foundation fail. So we are expecting this foundation, if there's a general shear, that's supposed to develop this particular, the particular spiral. So means the soil on that side is supposed to be pushing out. Okay, so what is the setup for this kind of the field test is what? You must have open a trench, the test pit, and you put a footing down here, and you start to have a clothespin over there, and you put some loading on the top, and you start to using this hydraulic jack to push the soil down. Okay, now here's a problem. If you are expecting this generation of the spiral gonna pushing the soil out, that means what? Your beam has to be long enough, so you have enough free space for the spiral to develop the free zone to push in the soil out. Okay, so size is a problem.
I don't understand your longest part.
What?
Yeah, this disturbance will be there.
Okay.
So you can continue.
Okay. All right. Sorry
I
for that.
request all the participants to keep yourself muted.
Okay. Yeah, I think a lot of people logged in without the mute. Okay, let me just keep going. Anyway, so the main problem we have here, you can see that the size of this foundation is a big issue, because when you have the bigger size, that means what? The beam has to be long enough to open up the space for this envelope to develop. Okay, so that's one of the challenge. That's one of the challenge. So you need to have a really, really long beam with a very, very strong hydraulic jack to push the soil. Okay, the other one it is, well, I just want to show you this picture first and I will come back. All right, so you can see this, the field test. So far you can see they have, those are, they call the loading plate. The loading plate is relatively very small. You can see this one only like a 2 feet, 0.6 meter, 2 feet, almost 3 feet, and so on. So probably up to only 1 meter, only 1 meter. So this is one of the reasons why they have this kind of small plate instead of our real foundation. I believe in North America, the shallow foundation normally is about 5 feet by 5 feet. If you are talking about a square footing, 5 feet by 5 feet is pretty much a standard. Okay, so basically this is a relative too small. Okay, so this is about what 3 feet, about 3 feet. So 5 feet to 5 feet, it's pretty much. And also you can see that the settlement, they push the loading plate down to only approximately about 4 centimeters, 40 millimeters, 4 centimeters. So 4 centimeters is about what? 2 inch, less than 2 inch, less than 2 inch. So relative, you can see that, well, this soil can probably keep going. For some of the reason, maybe your loading plate or your hydraulic jack is not strong enough to push the soil down. Or as I just mentioned, that you don't want to see the soil because some of the limitation of your the setup try to resist the soil to be freely to push it out. Okay, so that's one of the problem we have compared to the large scale we're supposed to have. For the pile, you can do that because the pile is relatively small cross section, right? If you're talking about the concrete pile, if the concrete pile is about 1 foot diameter, it's already pretty big. Okay, so pile, you don't have this kind of limitation, but a shallow foundation, unfortunately, because you are expecting the soil will be pushing out. The shallow foundation have this kind of push out zone, but the pile foundation, you're expecting the pile only goes straight down, right? Well, they will have a little bit, but you know, those kind of envelope is going back to the shaft itself. So they won't, the top, any structure above the ground won't affect whatever behavior for the shaft or the pile. Okay, so it's challenge to have the field test. Okay, and also you can see the one I'm just showing you right here. Well, when we have the settlement down to about like a 40 centimeter, 40 millimeter or 4 centimeter, it doesn't mean the foundation fail. The foundation is far from the fail. Okay, because you can pretty much predict this kind of line gonna keep going. They are not stopping. Okay, if you see the line is kind of tip over like this, okay, you can pretty much get some idea about, okay, you already reached the ultimate tensor, ultimate compression test. But seems like this line is still keep going. Okay, so this is not finished yet. Okay, so we are not really fail the entire soil. We are not really fail the entire soil. We saw some of the previous the field test. And the other one is soil suction. This is another issue we have. The soil suction. I think most of you already know that the soil, if the relative the sandy soil, and they will have some the soil suction, especially when it's partial saturation. But this soil suction can be changed very easily by the degree of saturation. Today we are pretty dry. Okay, you are expecting soil suction. The next day it rains and the water penetrates through the soil, get into your foundation, and it becomes fully saturated. And the soil suction, because it's fully saturated, and it's just gone. So soil suction is another problem we have to deal with later on. I will talk about this issue and how we can get rid of this kind of issue later, based on my our research. Okay. All right. So correction factor. Another one is a correction factor. Those correction factor, it doesn't matter it's from the MyHab, from the Basic, or from the Hansen. None of them have the test data to show you that it's really fit. So far, like Hansen and Basic, they have some of the loading tests, but those loading tests, the plate is only 1 foot by 1 foot, so it's only 12 inch. Okay, there's no test data is the size is larger than 12 inches so far. Okay, and again, this is the one I'm talking about, how to define what we call the true fail. The true fail, because as I just mentioned that most of our loading tests on the field, because of limitation of the power of the loading, the capacity, we never have the chance to see that how the foundation really fail. Okay, now let's talk about the soil suction a little bit. The soil suction, as I just mentioned before, that if the soil is partial saturated, it's not fully saturated, and when you run the triaxial test, you might have this kind of we call FAC. I use the FAC. I'm not sure if it's the right term or not. The cohesion you are seeing right here, but this cohesion will be gone because it's saturated. Okay, so the soil suction maybe will affect how we make the bearing capacity formula, because our bearing capacity formula, that's one term is CNC, right? So this C must be coming from this cohesion right here. And this cohesion, actually, if there's a the clay sand, and yes, that is a cohesion from the soil property itself. But if this is just only temporary, the soil suction, and they maybe will be over evaluate your bearing capacity. Okay, all right. So so that's one of the issue we have. The other issue it is, well, how we come up the friction angle. That friction angle normally is when you run the triaxial test, or maybe you run the direct shear, right? If you run the direct shear, you have a couple point and you try to get a best fit and get the cohesion here, get a friction over there. And for the triaxial system, you will get a 3 more circle or 4 more circle, but still you have to kind of like using your judgment call to get the best match. So after you do the best match and try to get the envelope, and that friction angle is always a question mark, because maybe this envelope is matching the first circle, but probably not matching the third circle or fourth circle, or maybe match the second circle, doesn't match the first circle, and so on. So this friction angle is always a question mark, because we, as an engineer, we always try to make it life easier, so you get a best match. So that's another issue we have. Okay. Now, so this is our proposal, how to get rid of the soil suction problem, or maybe some of the cohesion, even that's really the cohesion. I put a question mark. Why I say that the question mark? Think about the soil behavior. If we have a foundation here, we try to fill the soil along this spiral. Okay, friction is always there, not a problem. How about the cohesion? Cohesion we are talking about is like a glue between the particle and particle that try to stick together. The thing is, well, once your soil try to push the soil out, okay, in the very beginning, you can imagine that if you put your both hands together, in the very beginning, okay, it's kind of stick. But once you move a little bit, it seems like this cohesion is what start to either reduce or try to completely disappear, because your soil already moved. Okay, so this cohesion is always a question mark. When I talk to the some of the field engineer, sometimes they always ask me do I put this cohesion 100 pounds per square feet in the formula or not. My suggestion always say, well, if you have a friction angle is more than 30 degrees, forget about the cohesion, because I don't trust the cohesion will exist after the soil start to move. Okay. But of course, if you have a very low friction angle, that means what? You have a high percentage of a clay, and you have to rely on the cohesion. Okay, so it's practical side how you treat with the cohesion stuff. Right. But anyway, so this is our proposal. Well, since this is original, we are thinking about the envelope supposed to look like. So why don't we move this 0 down to here? So if I can move the 0 down to here and I just follow exactly the same slope, then I can get right up the C. So I start from this point. And of course, the convertible from this 0 down to this 0 prime supposed to be based on the cohesion it is divided by the tangent friction angle. Okay, so I just move my origin from this 0, original 0, down to here. So in that case, I can get right up the cohesion. I just only deal with the friction angle. So that's one of our proposal, how to get up the soil suction, and how to get up some of the cohesion, because we have 3 terms, right? Cohesion, CNC, QNQ, whatever it is. So if I can get up the C, that's make life easier. Okay, so this is one of our main proposal at this point. We try to shift the origin from original 0 here down to the 0 prime. Okay, with this dimension, of course. And of course, this C could be the soil suction. So if the soil suction is the same, it's a fact. Well, I won't say fact cohesion, but anyway, it is the number over there. Okay, you can get done there. All right, now, so another thing is how we really define the bearing capacity. The bearing capacity is supposed to be what we are talking about, the ultimate bearing capacity. So that means what? If you don't mind the settlement, you're supposed to be able to see the foundation supposed to be go down to some certain settlement and push the soil out. Okay, of course, we don't want to see the foundation entirely like a tip over and completely fail. But at least we want to see where it is. So that's what we call the real bearing capacity. Okay, this is the one from the pile. Yes, the pile can do that. So you can see that a lot of the pile foundation when they do the field test. This is pretty much the one we are expecting. When the piles start to get the loading, and then they will go down to the peak strands, not peak strands, it's peak strands, and start to what? It's either keep going or just finish like this. Okay, so it depends on the different soil condition, of course. Okay, so this is our goal, how to reach that point, because from the field test, we never get that point. All right. Now, the other one is, as I just mentioned, that we have to get the friction angle phi more accurate is from the triaxial test. Okay, and also the other effect is what? The type of a foundation. You are talking about ridge foundation, you're talking about flexible foundation. For example, you're talking about the water tank or oil tank. Okay, those 2 types of a foundation is we call relative flexible foundation. So they have some correction for that thing too. Okay, so we try to get rid of those kind of complicated case and try to make it simple. All right, the other one, how to define fail. That's an interesting question. Well, you can say that, well, for the practical purpose, I want to control the settlement in some certain range. Okay, fine. So here's our proposal right here. Well, it doesn't matter how you define the fail, your fail criteria it is. You can say, well, I want to have a 10%. I only take 10% of settlement compared to the size of footing. Okay, you can define as that. Or you want to have some we call the stress label. That means what? I want to know that, well, from one point to the other point, how much the settlement it is. And I want to define that one is a settlement. Okay, so you can use in the different definition for your different settlement. You want to define as failure criteria. You can use in the secant, you can use in the tangent, you can use in the we call the offset. Okay, so I will talk about this issue later on because it's something related to we call the elastic modules. Okay, all right, now let's take a look at this one. This is a Horng-Jyh of our proposal right here. Okay, so I think everybody see this kind of a diagram long time ago, and we know that if you dig some of the depths, and you put a footing back in and you start to carry the load. So whatever the total load we have here is we call Q ultimate. It's Q ultimate. So if you subtract this Q ultimate to whatever the overburden pressure here, that's what we call the Q net. Okay, so Q net basically is your Q ultimate subtract whatever B gamma X unit weight of soil and the depth of your footing. Okay, so why we focus on the Q net? Because think about this. Seems like when we take the soil, think about that we have to excavate this part first. And after you excavate this part, you put a footing and you put your structure on, right? So this Q net is actually a real difference. Compare the soil at this level, at the depth level, before and after you put a footing, right? Because before you put a footing, you already carry the much load on this particular level. But you excavate first, you put your foundation down, and you start to carry a load. So the Q net is the real pressure extra compared to before the excavation. Okay, so a lot of people like to take the factor of safety from where? From Q ultimate to whatever Q allowable or Q apply, whatever you put a loading on the top. That's one of the opinion. But some people like to use the Q net. Okay, so one way or the other way. Okay, now let's take a look what's going on down here. That's the most important part. So I believe most of you already understand that we call the active zone, the passive zone, and transition zone. So active zone, this part of the soil means what? The soil, because they carry the loading, so it's trying to pushing down. But this side, you can see above here, there's nothing except the overburden pressure right here, original overburden pressure right here. So basically, this part of a soil is under the what? Passive condition. So this part of soil was potentially trying to be pushing out. But between here, active zone and the passive zone, is something between. That's temporarily called transition zone. The transition zone right here. Okay, so it means I'm expecting this part of soil was pushing in and this part of soil is pushing out. So it's something between. So we just separate for these three zones. Okay, but most important is I want to show you that, well, what's going on here? This is the one we just take a small element probably on this the average depth. So here you can see that I'm carrying the vertical load. So this vertical load is no more than my entire Q ultimate. This is the entire Q ultimate. Plus overburden pressure from this point down to there. So this is the term right here. Okay. We can do this one in triaxial test, traditional triaxial test, not a problem, right? If you understand the triaxial test, you have the whatever the confining pressure it is, and you start to carry the load, and you get the deviatory stress. So this one is fine. That's not a big deal right here. Okay, how about here? That's the question mark. Because in here, your vertical effective stress is supposed to be consistent. But because the what? This zone of the soil tried to be pushing out. So you basically will be failed by what? That we call the lateral compression. So here is traditional triaxial system. We can run the test. We can have the whatever the confining pressure it is and start to carry the load. So we will fail the soil in this way. But here is quite different. The vertical is consistent, but the what? The horizontal is trying to push out. So this is something like this one. We still have a consistent vertical load, but is what? Is we call a lateral compression test. Lateral compression test. So how to run the lateral compression test in the lab, in the triaxial system? That is a challenge. But I think I do my Ph.D. work based on this diagram. You can see that, well, you can operate the triaxial test either do the compression or do the actual extension. That's not a problem. And also the same time, if I can reduce the confining pressure, normally the confining pressure is going down, right? So let's say if you have original, like say 2000 PSF, and if I can, what? Okay, Anyway, let me make it quick. You can reduce the pressure. Once you reduce the pressure, it's like a isotropic rebound. So we are talking about you compress the soil down to some certain of the confining pressure and you start to reduce. So this we call the isotropic rebound. So you basically reduce the cell pressure. So you will be able to get this one. So if I have this one, I have that one, this one subtract that one, that is this. That is this. It looks easy from the diagram, but reality, maybe you can control the strength. The strength is no problem. The strength is the problem. The strength is the problem. If you're interested, you can send me the email and I can send you my PhD work, some of my paper to explain how to predict the lateral compression from actual extension plus the isotropic response. Okay, so this is something my work. Okay, so anyway, so once we understand how to run the test for the actual load, okay, from here is a traditional actual compression, and this will be the lateral compression. And what's next? The next one is we try to put it in the more envelope and see what's going on. Okay, so let's see one by one. This one I'm talking about right here, the actual compression, the ultimate actual compression test. This loading will be come to here. Okay, so that is the point. How about the other point? I'm talking about this consistent passive zone, this point. This point will be here. All right, so now, if let's pretend this is your triaxial system, you find out the friction angle. I will talk about mobilized later on. So let's pretend this is the slope. So from here, of course, I can draw my Mohr circle, the maxima to touch the tangent touch the envelope to be the first Mohr circle. This one, the same thing. From here, I can draw my Mohr circle to reach my lateral stress. Okay, so this is the maximum circle I can go. So I would have one circle here that's under my passive zone. I will have this circle from active zone. So between the first circle and the second circle, that's a gap. Well, this gap we think is supposed to be transition zone. That means what? The one we are talking about right here. We are very, very uncertain that, well, what's really going on down here, where it is the active part or passive side. But anyway, in the Mohr circle, it looks like it's just between the two. It's just between the two. Okay, so this is something very interesting we try to propose and make the life easier. It is, well, I have the passive zone Mohr circle here. I have an active zone, the Mohr circle right there. So between that two, we just make a fact, use the fact, the Mohr circle, try to fit between the two, because I need that. All right, I will tell you why I need that. Okay, now next. This entire idea is from some of the pile foundation or shallow foundation. If you remember that we have a friction angle phi equal to 0, and the NC can be 6 up to 9. So what is 6 up to 9? It is what? If there's a 6, that means what? There's a 3 Mohr circle. If there's a 9, that means four and a half circle. 4.5 circle to reach from the confining pressure up to whatever the maximum vertical stress it is. So we are kind of like a good idea from here. So we try to propose this kind of Mohr circle behavior. If you understand the pile foundation, how it felt. All right, now let me tell you why I need that point, this circle, to help me to reach the bearing capacity. So everybody knows this formula. That's not a problem, right? How we can predict the major principal stress from the minor principal stress. That's your mechanics material stuff, right? All right, now, as we mentioned that, first of all, I get out of the seat. I move my 0 to 0 prime. So I don't need to worry about the cohesion or soil suction. I just only dealing with the friction angle. So first of all, this turn would be 0. If I move my origin original point from 0 down to 0 prime. So I can get rid of this. Okay, so this one will become 0 now. So this turns out. So I don't need to worry about that. Okay, then, as I just mentioned that, well, I will be able to know how much that point it is, right? That point it is how much the vertical pressure, oops, sorry. That's how much the vertical pressure right here. Overburden pressure down to the passive zone. Okay, so that's this point. That's this point. All right, now, if let's say that point, I put the Pingtung, okay, because we can calculate the pressure right away, even not doing anything, we can calculate how much the pressure it is. All right, so if I put this one right here, so this is my Pingtung, start. I put a start because I move by 0 from here down there, so the number will be a little bit different. Okay, so let's say this is a Pingtung. So if I put a Pingtung here, how much the major principal stress for that point? That would be what? This one, if I put this one as my 45 degree plus b divided by 2 is my failure angle, gamma, alpha f. So this become what? Pingtung star tangent square alpha f at that point. All right, so if I'm using this, we call fact circle, and try from this point to the next point, I can do what? Do the same thing. Put this term into your minor principal stress, you get a major principal stress here. So now it's power 2, now it's power 4. Similar, if I can predict this one as my minor principal stress under my active zone, then this Mohr circle, the maximum point will be what? It is my power 6. Power 6. This is very important because right now I just predict something from overburden pressure directly up to where? Up to my maximum ultimate bearing capacity point. And that is the point we are looking for. That is the point we are looking for. All right, QNet. So what is a QNet? QNet, we are talking about, well, if I take out my original overburden pressure, that's what we call the QNet. So the QNet formula is down here. Okay, now let's move on. So long story, I think I talked too much. All right, anyway, so that's our proposal, the QNet. The QNet is here. And because we moved that origin to the 0 prime, so this is the convertible and so on. All right, now let's talk about the mobilized a little bit. So what we call the mobilized condition, as we mentioned that, well, you can depends on how much the stress level you want to go, or you want to know a particular percentage of your strength. So you not necessarily always have to push the maximum to the maximum strength. So what's going on here? It is, well, use the same idea. Use the same idea. Now I can have we call the mobilized friction angle. So it depends on how far you want to go. Remember, we're just talking about you can have the secant, elastic modules, you can have a tangent, elastic modules, you can have offset elastic modules. So it depends on the stress level you can go. So even though this is your maximum ultimate tensile, bearing capacity friction angle, but you still can have some of the flexibility to predict if I want to have some of the lower stress level of the soil, the stress, and how much the bearing capacity for that particular point. We can use in the same thing. And also the factor of safety can define by, well, I can just very simply define by what? The friction angle between the two. Your mobilized friction angle to your peak. This is what we call the peak. The friction angle. And of course, you have to take a tangent for that thing. Or you want to use the traditional way, you can use in the QNet. The factor of safety is whatever ultimate factor of safety compared to the mobilized, we want to go for the stress level. Okay? All right. So Horng-Jyh is all in this particular the slide. This is the Horng-Jyh. This is the Horng-Jyh. Okay, so I put all the number together and I just put right here too. Because I only have a couple minutes left, let me just push very fast. And I'm very sorry that I maybe talk too much. too detailed, but I just hopefully everybody can understand. All right, so let's go back to the original and see what we do and what's the same, what's different. All right, so let's say the QNet, original QNet, supposed to be this. All right, so you put this one as we just talking about. It doesn't matter is a Teraki or from the MyHub and so on. This is the formula they propose. Okay, and of course we are not including any shear factor, incline angle, this and that, all the correction factor. We haven't. We just temporarily take it out. We're just talking about strength first. All right, now what's going on here? It is, well, if you see the bearing capacity factor NQ, NC, they all have some term. It looks like a similar. At least they are talking about the same thing, NQ minus 1 or NQ plus 1, whatever it is. Okay, so let's just temporarily put the NQ minus 1 and see what's going on. So this NC can be replaced by this formula. N gamma can be replaced by that formula, but it's all come back to NQ. It all comes back with the NQ. So if you put an NQ in one side and you take it out, So, well, you extract the NQ on one side, this one plus this one plus that one equal this. Okay, this is something we saw before. If you go back to my slide one more time, right here. Is that similar? It is similar, right? It's similar. And this is just I convert the what? That distance, right? I'm just bring down to here. Okay, this is original, this is how it looks like, the number it is, but because I move my origin from 0 down to 0 prime, so I need to plus this particular C divided by tangent phi. So this is the terms. Okay, so well, this is exactly identified as bearing capacity from these 4 people. Exactly identified. So this is our proposal. So why we bother? Let's just using this one. So this one actually is nothing but after I shift my origin down to the C minus tangent phi, and then I just need to know the what? The friction angle. Because this alpha F is what? 45 degrees plus phi divided by 2, right? So if I know this friction angle, and why bother? The bearing capacity is just right there. But once again, normally we get this friction angle is from the triaxial test. And the triaxial test, the friction angle is supposed to be what? Is only good for square footing or circular footing. If you're talking about long straight footing, you need to have some correction. You have some correction. Because when we run the triaxial testing, you are expecting the sample fail freely from different direction, right? But for the straight footing, we are expecting only fail in 2 dimensions, basically. You are not expecting to do this way, you only do this way. Okay, so you still can do it. Let me just very quickly. We still, if you want to deal with the straight footing, remember, normally in MyHub or from Teraki, if you have a long straight footing, you don't need to do any correction. But this is kind of opposite side. Well, if you want to deal with a long straight footing and you need to have your triaxial friction angle you are getting from your test, and using this formula to convert the friction angle you are using for our proposed formula. Okay, so what's the benefit so far? Is we get rid of all the different correction factor for the shape, and get rid of all the correction factor for the depth. But we haven't talking about is a correction factor for the incline angle or on the slope. No, we are just only talking about the normal condition. You are put a footing on the flat surface. That's it. We couldn't prove that it is good for the incline angle, or you are putting the slope on the slope, the foundational slope. Okay, so I'm not talking about a particular issue. Okay, let me just very quickly to go down some. All right, for the strength. Oh, this is another issue we have. Anyway, so this is the idea we have. Okay, So because when we're talking about foundation fail, let's suppose we fail immediately. So we are not talking about the settlement. We are talking about immediate settlement. We are not talking about consolidation. So immediate settlement, we come up this idea. We are kind of like follow the same, they call the strain wage right here. So if you see the formula from schematic, it is also, he didn't use the strain wage, but actually it's a strain. Why? Because this is actually the pressure. This is the pressure. These are elastic modules. So this one divided by that one is what? Is your strain. But of course, he introduced what we call the influence factor. The influence factor. So from the different depths they are trying to do, they have a different, they call it influence factor. Okay. But anyway, let's move on very fast because I'm kind of running out of time. I know that. Let's just very simply take one of the particular Mohr circle and see how we can using that particular Mohr circle to predict the strength. Because once we can predict the strength, we will be able to predict the settlement. All right, so here we go. This is the Mohr circle under our the active zone. Okay, that's the last circle we're just talking about the bearing capacity, right? So again, you can, based on the stress level you want to go, you don't need to necessarily always go up to the maximum ultimate bearing capacity. You can something lower. Okay, so this is your the triaxial testing you're expecting from the normal drain test. So of course, lower confining pressure have a lower maximum compression stress. The higher confining pressure, you have a higher one. So the same thing for the Mohr circle. If you have the lower, relative lower confining pressure, your Mohr circle is smaller, and this one will be bigger. Okay, but anyway, from here to here, you are talking about deviatory stress, right? From here to here, you're talking about deviatory stress. So you're talking about, for example, you have a confining pressure at this circle, this red dot right here. This is from here. So you are generate this Mohr circle, this envelope right here, stress strain curve. Okay, and based on the stress level you want to go, or let's say I want to have a 2% of my strength only. So this is your 2%. You shoot up, you shoot over, you get this particular point, and then you can using this one as your secant elastic modules. So this is secant elastic modules. So what's going on? The strength is supposed to be what? The deviatory stress is equal to your elastic modules multiplied by your strength. So basically your strength is what? It's your deviatory stress divided by your secant modules. Your secant modules. Okay? And we do this one every single level down to what? Whatever this strain wave is supposed to go. So based on the Schutzmann's suggestion, if I have a square footing or circular footing, it's only good down to about 2B. If you are talking about long straight footing, you can go down to 4B. You can go down to 4B. Okay, so we do the same thing right here. So if I'm dealing only well for the square footing or circular footing, I can start to accumulate the strength down here, down to 2B for the square and circular footing. But if I want to go down to 4B, that's for the long straight footing. So I just accumulate the strength, whatever I have, then I will be able to predict the settlement. Okay, 1 minute left. I'm sorry for that. Talk too much. Let me just show you the result. Anyway, and this is how we predict the strength based on Bolton's equation. But we also come up our own formula to predict the Epsilon 50, because the Bolton equation right here, they need to have a strength at 50% stress level. 50% stress level. And Dr. Norris, actually, this is his work, his PhD work a long time ago. He came up this particular Epsilon 50, the formula to using a different CU. That's but you need to have the sandy soil, only good for sandy soil, and you predict the Epsilon 50 based on his work. Okay. We're using the Texas A&M. They do the field test. The good news, okay, let me finish this one with the good news. You can see the size they use. It's much bigger. Okay, they have about 1 meter up to 3 meters. Finally, some people do something good. Okay, this is about 1 meter. This is about 3 meters. So relative, it's good. It's good. But unfortunately, something not good is what? They buried the loading plate too shallow. You can see this one only 0.7 up to about 0.8. So you're talking about 2 feet below the surface, or like 2.2 feet, 2.5 feet, about that range. Okay, so something good, something not good. The good thing is, well, they basically have really good size of the loading plate, but for some reason they didn't bury deep enough, and they also take the borehole to do the Brokan test and get a Brokan number. So we're using the Brokan number to convert the friction angle down there. Okay. All right, so let me just very quickly to show you the result. All right, so anyway, you can see this, the pink line we are showing right here is their major data. This is their major data. The one with the dashed line is we're using our formula to predict what is the loading versus the settlement. Okay, so you can see they are kind of stopped right here. They are stopped right here. Test data stop right here, but we will be able to extend all the way down there. So this is test number 1 with size number 1 by 1, 1 meter by 1 meter. This is the major. This is our bearing capacity, simple way to predict the loading versus the settlement. I won't say 100% match, but it's pretty good. This is, we try to compare what we have to the Taraki, Packenson, and other people's. We just only compare the bearing capacity instead of the settlement. They didn't predict the settlement, so we just try to compare the bearing capacity. This test number 2 with a little bit bigger size, 1.5 by 1.5. Okay, and then when they go into test number 4, they have a bigger size. But you can see this one is kind of short. The reason is what? Because once you have a bigger size of the foundation, of course, you need to have a more higher capacity for your hydraulic jet. And also, as I just mentioned, that you might have to have the longest the beam to allow the soil to push it out. So you can see the settlement is kind of very limited. And also, you can see this is not even close to the ultimate bearing capacity. They stop right here. But we will be able to predict all the way down. Okay, and so on. All right, and also we try to, let me just very quickly put all the together. This 1, 2, 3, 4, 5 is from the Texas A&M test. This 6, 7, 8 is from the textbook from both fourth edition. And we try to compare using our model. This one only compare the bearing capacity, not including the settlement. Okay, so the bearing capacity we have is right here. We get this one is close to the one is supposed to be major. This is the one. We get this one. We get this one. We get this one. We get this one. Okay, so out of 8 tests, we have a best match 1, 2, 3, 4, 5. 5 out of that. Okay, but the other is not that bad. It's not that bad. Just a little bit off. I mean, compared to the other. The data like this one is supposed to be the major is 24.2, so we pick this one as a winner. But actually, we get the 25.4. It's not that bad because the factor study we are taking what 3.0. So 3.0. If I'm talking about 3.0, that's nothing. Okay. So I just want to present that this particular presentation. I'm sorry it's taken me too long to. I do have some other stuff to go, but unfortunately, I probably the first time do the this thing. It's not really okay. All right, so all right. Is there any question I can answer?
Yeah, I think you were on time, Dr. Yang.
Oh, really? Okay. Oh, I'm sorry. I cannot talk too much.
Yeah, we have enough time, so we can take question answer session.
If the time is an issue, I will welcome everybody try to send me an email. I do have my email right here, and my advisor, Dr. Gary Norris. I would like to answer all the questions through the email if you prefer, because I know you might have a next schedule is going on.
No, no, we have only your session
Oh,
today.
okay. All right.
So because here we are enjoying our Sunday, so um, so we have only your session, but tomorrow onwards we have 4 sessions per day.
Oh,
So
okay. All right. So
so
maybe I can take some question
yeah,
right now.
you can take you can definitely take questions. And
Okay.
first of all, I was really impressed and I was amazed to see that you were able to get rid of some of the things like shape factor and other issues that are there. Definitely, it is one of the uh, challenging problem estimation of load carrying capacity of shallow foundation. And
Mhm.
somehow we have mixed up the things. I still struggle that why there are separate calculation for settlement and separate calculation for shear for failure. Like, and can't we combine these two? Because now we have all constitutive models and we have stress strain behavior. And from the single stress strain curve, we can actually do a lot of things. So uh, that is my idea. But then see that you have very well addressed a lot of issues. Majorly you are able to get rid of this C component. That's
Yeah, that's the one of our
interesting.
purpose because the
Yeah,
soil suction is always an issue.
yeah, always an issue. And then people get actually confused, like because even I find very difficult to tell my students that these C and Phi are not geotechnical properties. They are just parameters and they depend upon type of test. Even for sand, if you perform UU test, you are going to get C. For clay, if you perform CD test, you are going to get Phi. So they get confused. So, and they try to relate C with the clay soil and cohesion and Phi with sand and then angle of friction. So like that, but then it was great to see that at least you are able to get rid of one parameter. That is C. And I'll just take up some questions that has been asked with participants. One question is
Mhm.
asked by uh, Franco Macias. He is asking what friction angle do you recommend for bearing capacity calculations, whether
Okay.
peak
That
friction angle or constant volume critical friction angle.
okay. That is very very good question and always a challenge for people to think about that. Well, I'm not sure how familiar most of people know the soil behavior under the dense condition and medium dense condition and even the loose condition. We are talking about dense condition. We are talking about relative density at least 85% and above. So if you have that kind of a soil condition, you are expecting your stress strain curve is going very quickly go to the peak and then start to drop down. All right. Now here's a problem we have. If you're talking about the foundation, well, this is a kind of practical question, not academic side. Um, it depends on what you think about your seismic load. So if you're talking about you are expect to have the foundation can survive during the liquefaction, I will probably suggest we take the residual one because the residual one you are expecting the strength is going all way beyond the peak strength. So it really depends on the location you try to put your foundation. If you're try to survive during the liquefaction or partial liquefaction, that kind of condition, I might suggest you have to take the residual one. But if you're just only in a regular two storage building and maybe just a house, I would say just go ahead get the picker strengths because since we take a factor of safety equal to at least 3 in North America, so even though you take the factor of safety 3 with a peak strength, it won't go anything wrong. But as I just mentioned, that if you want to survive during earthquake, maybe you take the residual one because you can allow your foundation to have a larger strength. Hopefully, it helps.
Yeah, I think you have answered the question well. I can see some other question. What is the upper and lower phi value valid? Valid
Uh,
value of lower and upper phi.
Can you come again because the
Yeah, it
voice
is
is
asked by Jigisha Vashi. Maybe if she is here, she can unmute and she can ask the question because question is not clear.
Yes, please go ahead. Unmute yourself because I tried to tracking down the chat room and see.
Then there are questions from Rajul. Any modern machine techniques we can use settlement in foundation or bearing capacity of soil?
Oh, okay, that's very interesting. Let's say this way. Um, if you understand that there's a lot of research right now going on, and not only just a research part. Actually, the industry side also try to using the geosynthetic, geotextile, geogrid, try to reinforcement the soil beneath the foundation. So I believe I won't say it's any good techniques right now to improve the bearing capacity. But I believe those kind of soil reinforcement down the road, not using the chemical, I'm talking about those plastic product. It could be very, very useful. And I hope some of the research can keep going on and with some standard design manual for the practical engineer who can modify their, well, pile foundation is not an option, of course, but normally the pile is kind of expensive. Um, and also a lot of uncertain thing. And actually, Dr. Norris also have some of the opinion about the settlement for the pile foundation, and especially for those the tower, the what's it called, the wind power, the tower have a dynamic load on the top with a circular seismic load. That's also another of the pile foundation settlement. We maybe can down the road to do some research about that. Another one I want to kind of like emphasize SBD Brokan number. Okay, now as academic side, we know that the SBD Brokan you supposed from the field Brokan number and you convert to N60, and from N60 we correct from N60 to N160 because all the research for the friction angle, for the bearing capacity, or from even the settlement, most likely they are all based on the N160. But here's the thing. Well, the 60 it is because we in the past, in a long time ago, I think back to the Taraki Hansen their time, they always using the labor to run the Brokan test. So that's why they only rely on 60% of the energy efficiency. But now pretty much everybody, especially in North America, we use the machine all the time, use the diesel engine and leave the hammer all the time. So the formula they try to convert N60, whatever the Brokan we have on the field, to N60. That formula always drive me crazy a little bit because it seems like we have a Brokan number, let's say 25 on the field. But after you have 90% of energy efficiency from the diesel engine, and you're talking about from 25 suddenly pop up to 31, 32, about the range. So you're talking about from medium dense to at least dense or very dense condition. So I kind of like sometimes don't really like the SBD Brokan number, the old formula we try to convert. But of course, this is rely on another research. Hopefully, some people will come up with the idea how to more realistic right now in the 21st century have instead of N60 and we can have like N90. They kind of the formula directly.
That is true. Lot of things has to be done, and
Yes,
I think
geotech is
they have
another
given
thing.
lot of information to the young researchers and practitioners, and mainly students who can take up your work and they can also start thinking in the direction, and maybe they may join you also, and they will work with you to understand more and deeper into the problem statement. I think it was amazing to see all equations, questions, and other things that you asked in a very nice manner. And you actually addressed the issues that are there in the area. So I can see a few more questions that are there, but that are not related to your presentation. But still, I will read and I will seek your insight on the issue that presenter has asked. Like, can we reinforce the soil with layer of piece of papers, and can we increase the strength of the soil?
That's a very interesting question, because sometimes I conduct the summer camp for those kind of kids, and I told them to make a sand cake. I use the cake. So basically, they have a PVC pipe, and they put some of the moisture soil in there and make a cake. And the other group, and they just put a piece of paper just between the different layer, and we try to put a loading on top. And those pieces of paper actually provide pretty good strength.
They create wonder.
They kind of like soil strength. It's very interesting, and I hope hopefully some people, if you're interested, you can try that with your kids, and it's kind of interesting.
Yes. Yeah, when it comes to increasing the strength, definitely the piece of paper is going to, because you are actually reinforcing, so it is going to improve the strength. But now, then you have to see the biodegradability aspect also, because paper will not be able to survive for a very long time, and then with time it will lose, the soil will lose its strength. So it's good for playing, but not for putting below your foundation.
Yeah.
There is another question, interesting question from the participant.
I would love to share the presentation slide. So maybe I will convert to PDF file. I will send to you.
Okay, one request was there. Yeah, one request was there from the participant that if you can share your presentation. So you can share the presentation with me, and then I will circulate the participants. And that is one thing.
Oh, I saw a question here. It's very interesting regarding the soil suction to N60 value. Wow, that's a fantastic question. Now, I'm not sure is that any one of you ever heard about you supposed to correct your blow count number under the groundwater. Actually, if you run your SBD blow count under the groundwater, well, when you drill the hole, obviously, if you leave the hole for a certain time, and groundwater will definitely seep in. And when the groundwater seep in, when you run the SBD blow count on the top, you must be correct that, because some of the energy, instead of absorbed by the soil itself, it was absorbed by the water. So even though, so that's why I kind of sometimes put a huge question mark on the blow count number N60 out there. But practically, because I also a licensed engineer here, so time to time I do some consultant work. It's very interesting if you tell some people, say, okay, the blow count is 30, 35, automatically when you do the design, you kind of drop it down to something. You actually are supposed to increase, because we try to convert N60 to N90, right? 90% of the energy efficiency. But a lot of geotechnical firms, especially local, they more rely on their experience. Okay, so the number we get from the field not necessarily really affect in the design part. Soil suction, it is a problem, because once the soil suction kicks in, you are expecting your blow count will go higher, because the soil suction basically try to increase your soil strength, right? But it's temporary, as I just mentioned in my presentation. We are talking about groundwater go up and down all the time, right? Dry season goes down, the frost season goes up. So I would suggest, if you have a soil suction, the kind of the condition, you may want to wait. So what I'm saying, the want to wait is, after you dig the hole, I believe this local area, most of people have the common sense about how deep the groundwater table it is. If you know how deep the groundwater table is supposed to be, and you might wait for the groundwater seep into the hole, then you run the test. Okay, do not just dig the hole and run the test right away, because that's sometimes the soil suction is going on, and you will miscalculate the higher stress.
That is true. That is true. So I think we are getting very good response from the participants. They are very much happy and satisfied with your presentation. They are giving excellent feedback of your session. So now I will, because there is no more question for you, so I will request my co-chair, Mr. Pranjal, to give vote of thanks and close the session.
Thank you.
Thank you very much, sir, for taking up the queries of our audience on behalf of School of Civil Engineering, Lovely Professional University, IGS, Jalandhar Chapter, and Department of Civil Engineering, NIT Jalandhar. And from the entire team of faculty members and students, I am thankful to you for spending time with us. We wish you all the good health and prosperous life ahead. As a token of appreciation, please accept our e-certificate of appreciation.
Thank you, everybody. I'm really honored to be here, and hopefully I can get some feedback from audience. If you have a research or you are interested about the bearing capacity down the road, and you can email me or email Dr. Gary Norris, and we'll try to help out. And hopefully our paper will be able to push through some of the very tough questions and be published soon.
Thank you, sir. Thank you so much.
So I'll just put that certificate on the screen so that audience should. So can you see that presentation? This e-certificate of appreciation from our side. So this is
Yes,
from.
I can see that. Really nice. Thank you.
Thank you very much. This is our lovely university logo and NIT Jalandhar logo and IGS Jalandhar chapter logo. With that, we wish you all the best and thank you very much for being with us. Thank you, Dr. Yang.
Thank you. I'm very happy.
Thank you, sir.
My power is still on. My internet is still on.
Oh, yeah. So thanks a lot. We are signing off now. Thank you very much.
Okay, thank you.